All right, let's get right into it. For thousands of years, we thought we had the heavens all figured out. But there was this nagging problem. Our observations, what we could actually see, never quite matched up with what we believed. This is the incredible story of how one stubborn planet and one brilliant, persistent mathematician completely rewrote the rules for the entire solar system. Ever since the ancient Greeks, the circle was seen as the perfect shape, divine even. And the heavens, well, that was the realm of perfection. So it just made sense that planets would travel in these beautiful, perfect circles. The only problem was, they didn't. When you actually tracked them night after night, they just refused to cooperate. They'd speed up, they'd slow down, they'd wander around in ways that a simple circle just couldn't explain. And the biggest offender, the real problem child of the cosmos, was Mars. Astronomers tried everything. They cooked up these complex models with circles within circles, circles off-center, but no matter how they fudged the math, the position of Mars in the sky was always, always off. The data was practically screaming at them that something was deeply wrong with their core idea. So, to crack a puzzle this big, you're going to need a special kind of team. It called for two very different types of genius. You needed someone who could get the best, most accurate data the world had ever seen. And then you needed someone who could look at that mountain of numbers and see the hidden pattern, the music within the noise. And here are our two heroes. On one side, you've got Tycho Brahe. He was this wealthy Danish nobleman who spent decades making these incredibly precise observations of the planets. And get this, he did it all before the telescope was even invented. He had the best data, period. And on the other side, you've got Johannes Kepler, a brilliant but kind of broke mathematician hired by Tycho to do one thing, make sense of all that data and finally solve the infuriating riddle of Mars's orbit. Now, Kepler was sure he could solve the Mars problem using circles. He was a deeply religious guy who believed the universe was this divinely ordered, harmonious place. But the data was about to force him to make a revolutionary break with 2,000 years of thinking. For years, Kepler just crunched the numbers. I'm talking hundreds and hundreds of pages of tedious calculations, trying with all his might to make Mars fit a circular path. At one point, he was off by just 8 arc minutes. That is a tiny, tiny error. But Kepler trusted Tycho's data too much to just sweep it under the rug. And then, in this amazing flash and insight, he realized maybe the problem isn't the data. Maybe it's not my math. Maybe the whole assumption is wrong. Maybe the orbit just isn't a circle. And he found the shape that fit the data perfectly. It wasn't a circle, it was an ellipse. You can just think of it as a squashed circle. And an ellipse has these two special points inside it called foci. Here's the kicker. Kepler discovered that the sun wasn't sitting right in the middle of the orbit, but at one of these two focal points. And boom! That became Kepler's first law of planetary motion. It was an absolutely radical idea that just shattered that ancient belief in perfect circles. The heavens weren't circular after all. They were elliptical. Okay, but changing the shape of the orbit creates a whole new puzzle. If a planet is sometimes closer to the sun and sometimes farther away, does it always move at the same speed? Kepler was pretty sure the answer had to be no. That's the next logical question, right? A perfect circle suggests a nice, steady, constant speed. But an ellipse? Well, that implies something way more interesting is going on. So Kepler discovered this other beautifully simple rule. Picture a line stretching from the sun out to a planet. As that planet moves along its orbit, that line sweeps out an area, kind of like a windshield wiper, or like a slice of pizza. What Kepler figured out is that the planet sweeps out equal areas in equal amounts of time. So look at the picture. For the planet to sweep out that long, skinny slice when it's close to the sun in, say, 30 days, it has to be moving really, really fast. But to cover the same amount of area when it's far away, that short, fat slice, it has to be moving much, much slower. We actually have a name for this point of closest approach. It's called perihelion. This is where a planet puts the pedal to the metal and hits its top speed for the year. And the opposite point, the one farthest from the sun, is called aphelion. That's where the planet is just taking a leisurely cruise. So, all the planets are in this constant dance of speeding up and slowing down, all year long. So, by this point, Kepler had nailed down the shape of the orbits and the changing speeds of the planets. But he was still searching for that one final piece, a unifying law, a mathematical relationship that would tie the whole solar system together in that divine harmony he was so convinced had to exist. And this is where we get to see the data just like Kepler did.
He took a planet's orbital period, how long it takes to go around the sun, let's call it P, and its average distance from the sun, A. Now, at first glance, those numbers don't look related at all. But then he tried something. He tried squaring the period and cubing the distance, and suddenly, just look at those last two columns. For Earth, for Mars, for Jupiter, for every planet, the numbers are almost exactly the same. It was right there all along. This was the hidden harmony he was looking for. And that became Kepler's third law. It's this simple but incredibly powerful equation that connects a planet's year to how far away it is from the sun. It proves the solar system isn't just some random collection of stuff. It's a beautiful, orderly system governed by a precise mathematical rule. So these three laws, they weren't just clever math tricks. They completely change how we see the universe and really our place in it. I love this timeline because it shows you how science is really supposed to work. First, Tycho gathered the data. Then Kepler came along and found the pattern in the data describing what the planets were doing. And then, decades later, Isaac Newton built directly on Kepler's laws to finally explain why they were doing it with his universal law of gravitation. Kepler was the absolutely essential bridge between pure observation and modern physics. When you get right down to it, Kepler's entire struggle is the story of modern science in a nutshell. It's about having the incredible courage to throw out a beautiful, cherished theory, the perfect circle, when the hard evidence, the cold, stubborn data, tells you it's wrong. It was a total victory for observation over dogma. And even though the story is 400 years old, it leaves us with a really powerful question. Kepler's genius was questioning an assumption that literally everyone else took for granted. So it makes you wonder, what are the perfect circles of our time? What ideas are we all just assuming are true, waiting for a modern-day Kepler to come along with the right data to show us we've had it all wrong?